Welcome to the Explainer. Today we're going to tackle a concept that I know sounds a little intimidating, but trust me, it unlocks this incredibly visual and powerful side of math. We're talking about complex numbers.
All right, let's just dive right in with a question that seems, well, impossible in the world of numbers we use every day. What is the square root of -1? I mean, think about it. If you try to solve an equation like x squared equals -1, you just hit a brick wall.
And here's why. You take any real number you can think of, positive or negative, and when you square it, you always get a positive result, right? So something like x squared plus 1 equals 0 just seems completely unsolvable. And for centuries, that's exactly what it was, a total mathematical dead end.
So, you're at this dead end. How did mathematicians get past it? Well, they came up with a pretty radical what-if scenario.
They basically invented a new number. They called it the imaginary unit, or just I, and its whole reason for being comes down to one simple but super powerful rule. I squared equals -1. Now don't get hung up on the name imaginary. It's not imaginary like a dragon or something. Just think of it as an expansion of our number system, a new tool in the toolbox.
So once you have I, this opens the door to a whole new kind of number, the complex number. We usually write it as z, and it's made of two parts. You have a real part, a, and an imaginary part, b. And you just stick them together in the form a plus bi.
Okay, so we've got this number now, and it has two totally separate parts. How on earth do you draw a picture of that?
And answering that question, well, that's where the real magic starts. This is the moment we jump from just crunching numbers in algebra to actually seeing them in geometry. And believe me, it changes everything.
You know our good old number line, right? That single horizontal line. It's perfect for real numbers, but it's got no room for that second imaginary part. It's totally one-dimensional. So it's pretty clear, a single line just won't cut it. We're going to need another dimension.
And the solution is brilliant. It's called the Argand diagram, or you'll also hear it called the complex plane. All we do is take our familiar horizontal axis for the real part, and we add a vertical axis for the imaginary part. Simple as that.
And bam, just like that. What was this abstract idea, plus bi, suddenly becomes a real, tangible point on a graph. It's just the point a comma b. The real part is your x-coordinate, the imaginary part is your y-coordinate.
This new 2D perspective reveals something absolutely incredible. It turns out that doing math with complex numbers isn't just about following some abstract rules. No, they're actual geometric transformations that you can literally see.
Let's start with addition. That's the easy one. Adding complex numbers? It's really just like picking up the point on the graph and shifting it around. It's a simple translation. That's it.
But multiplication? Oh, multiplication is where things get really cool. When you multiply by a complex number, what you're actually doing is a combination of rotation and scaling. You're spinning and stretching the point on the plane.
Okay, let's actually see this happen. We'll start with something super simple, the number 2. Now, on our complex plane, that's just the point 2, 0, sitting right there on the real axis. Now watch this. Let's multiply our number 2 by I. What do we get? We get 2i. And where's that on the graph? It's the point 0, 2. So what just happened? Our point just rotated a perfect 90 degrees counterclockwise. Okay, let's do it again. Let's multiply 2i by I. That gives us 2i squared, and what did we say I squared was? It's -1, so our result is -2. And look at the graph. Geometrically, that's another 90-degree rotation. We've landed right on the point -2, 0.
So here's the big takeaway. That rule, I squared equals -1, it isn't just some random definition a mathematician made up. It's a geometric fact. Multiplying by I twice is a 180-degree rotation. It's what flips a positive number to its negative twin on the other side of the graph.
All right, next section. Now that we have this geometric picture, it lets us measure these numbers in two really important ways, by their distance and by their direction.
First up is something called the modulus. You'll see it written with these vertical bars around the z. All it is the distance of the complex number from the center of the graph, the origin. It's the number's length, or magnitude. And hey, it's super easy to calculate. It's just the good old Pythagorean theorem.
Now, here's a common trip-up. People sometimes think the modulus, the length, is itself a complex number. But nope, it's just a length, right? So it's always just a single real positive value. That's it.
Okay, the second way we measure is the argument. If the modulus was the distance, the argument is the angle. It's the number's direction. We measure it starting from the positive real axis and then sweeping counterclockwise until we hit the line that connects our point to the origin.
And there's a really solid 3-step process for finding this angle every time. Step 1, you calculate a sort of reference angle. Step 2, you figure out which of the 4 quadrants your point is in. And step 3, you use a simple rule based on that quadrant to find the final correct angle.
Yeah, this diagram might look a little busy at first glance, but the idea behind it is actually super simple. All it's showing is that depending on which quadrant your number falls into, 1, 2, 3, or 4, you just use a slightly different rule to adjust that reference angle. It's a totally foolproof system for nailing down the number's exact direction.
So think about where we started. We had an equation that seemed like a dead end, totally impossible. And just by having the guts to invent a solution, we unlocked this whole new, rich, two-dimensional universe. A universe where numbers have both distance and direction, and where multiplication is just rotation. It kind of makes you wonder, doesn't it? What other ideas that seem impossible today are just one simple shift in perspective away from being understood?